Okay, let's start with the situation where we have, okay, a characteristic equation where we have a parameter alpha, and the parameter is not in the normal way. It's not like the K, for example. We did all of our rules and rules based on, okay, let's say the loop gain, okay, equal to 0. So K is multiplying the loop gain. In here, I'm having alpha. Alpha could be, parameter in the as 0 or, a pole. So how do I address such situation? We said, okay, in the root locus, you could have the gain or any parameter in the system. So if we have this situation, what do you think? How do we address this situation? Well, what we try to do, we try to convert the characteristic equation into something similar to this one. So let's cross multiply. So if you cross multiply, this is what you get. Now arrange the polynomial without the alpha and with the alpha. That's basically, I will have, I can rearrange it like that. I will have s cubed and this s squared 1, and then the other, which will be the coefficient of the alpha. I want it in this format. So what do I do? I want it to be in the format K times the loop gain.
يعني L of S, دكتور, there shouldn't be any alpha inside L of S.
No. Yeah, alpha will be out. But what's important, you want 1 in here. How do I get 1 in here?
You have 1.
Divide by this quantity. So what do you get? You get 1.
Yes, you're right. You're right.
Alpha S, this S squared plus S plus 1 over S cubed plus S squared plus 1 equal to 0. Okay? So now I'm not going to go and sketch it. You proceed from here. This is exactly what we have been.
So we always, Doctor, go to the fundamental way of expressing the.
Yes, I mean the basic, because our all the rules which we built based on this equation. So put it in this format. Okay. Now the question is, what will happen if I have, let's say, 2 parameters, alpha and beta? How do I, root locus is designed for 1 parameter, K, alpha. Now we have, can I use the root locus for 2 parameters? Okay.
We have to fix one and vary the other.
Exactly, exactly. I cannot vary both of them at the same time. So let me assume that I would like to vary beta and fix alpha. So let me rewrite it as in this format. So in this case, I'm assuming alpha is a fixed number and this is beta. Or, okay, look, if beta equal to 0, what will be the roots of the characteristic equation?
If beta is equal to 0,
what
there will be a contradiction.
No. Take it from here. I know. I mean, you are going to tell me 1 equal to, well, take, okay, beta equal 0.001, I mean, very epsilon, or take it from here.
Yeah, so because we divide by s cubed plus s squared plus alphas will be 0.
So basically, if beta equal to 0, what will be the roots of the characteristic equation? It will be, this is the root of the characteristic equation,
Yes,
isn't it?
right.
So,
Yes, you're right.
okay, so I will have s cubed plus s squared plus alpha equal to 0. I'm fixing beta to be 0. Let me do the root locus for this one.
So we divide again by s cubed plus s
Exactly.
squared.
So 1 plus, okay, alpha 1.
This is for only beta equal to 0. For first
Exactly.
beta. Yeah.
Okay. S squared plus 1 equal to 0. So if I want the root locus for this one,
You have 0 whole and
okay,
you
I
have
will have
minus
a
j
0.
omega plus j omega.
Okay. And go to be something like this. Wait a minute. Yes. I did a mistake here. It should be.
دكتور صوتك راح بعيد شوي.
دقيقة شباب. I have, this is the situation. So 1 plus alpha s square. I did a mistake in my. Okay, this
بس
is.
اس سكوير هذه بس يعني
Yeah,
بدل
s square.
طيب يعني.
Okay, I did a mistake. So it's going to be, I will have double pole in here and a pole in here. And if you graph them, this is basically the graph for alpha with beta equal to 0.
وكيف سوى هذا الكيرف؟
So now, كيف؟
الكيرف كيف سوى هذا في الرايت؟
Oh,
هذا بلين.
easy. عبد الرحمن. Okay, let me clear and I will let me do it. This is what we have. Where are the poles? How many poles I have? 2 in here.
Yes.
1 in here at -1. Now, first of all, which part of the real axis on the locus?
يفترض بيكون في الاود واللي so yeah.
Okay. How many asymptote I should have?
We should calculate them using
How many asymptote? How many poles? How many zeros at infinity?
شو اسمه one asymptote or two asymptotes.
ايش نفزور؟ we have 3 asymptotes. The difference between the poles and the zeros. I don't have any.
We don't have zeros. We have three
Exactly.
poles, so 3 asymptotes. Yeah.
3 asymptote. Okay. So 3 asymptote. Now the intersection, okay, sigma A equal to, okay, -1 over 3. So it's going to be somewhere in here. What about the angle of asymptotes? The angle will be 60, 180, 300. So this will leave in this way. And that's why we have it in this way. Maybe the confusion in the direction of alpha should go in that direction.
بس احنا دكتور عادة كنا ناخذ الروت لوكس from الزيرو للبول صح؟ الاود نبدا مثلا لو كان عندنا زيرو.
No. You start with pole, you end at 0.
If we don't have zero, so into infinity خلاص ما
We go to
عندنا.
infinity direction. So now look. Let me select alpha, this value. Now go back and do the root locus for beta. And this is the root locus for beta. Because I will have a 0 at 0 and 3 poles.
This is only for alpha 1.
Exactly. And so it's going to be that's straightforward. If Now change alpha, you get another set. Or somebody asked me if we can start with, at the beginning, rather than starting with beta, start with alpha. You can do the same. So what I'm trying to say, if you have two parameters, you change one and do the other, and so on. It's not going to be that straightforward, but it is doable. It will be parameterized as if. Most of
طيب سؤال الآن
تفضل.
تفضل الآن في الماتلاب مثلا أو any software مثلا if they want to visualize يعني many values of beta and many values of alpha to see kind of the intersection region between them or the region that will satisfy the stability. So they will do it they will plot it in 3D, for example.
Yeah, most
beta
likely, yes, you are right. You are right. It will be 3D. It will be 3D. You can visualize it on 3D.
And then
But okay,
found
but
the
what will
grid.
happen? Okay, suppose I have, how about if I have 3 parameters or 4 parameters or 5?
In this case, you need
Yeah,
a tensor.
it will be, but yes, you are absolutely right. Look,
Yeah.
if it's 1 parameter, it is, yeah, just simply plain, okay? If it's 2 parameter, yeah, definitely it will be 3-dimensional because, you know, I mean,
Yeah.
each time you are saying one and you are getting one once, I mean, you are going to get a set. And for this set, you have to have, you know, for each one of them is going to give you care for the other. I agree, it will be 3-dimensional. But again, as I said, this, you know, what we want to just, you know, there is an example in the with the slide, you can go through it. They use it in the design. What I want to, you know, I want to move to another topic which is very important because again, we are, who said we should follow the syllabus? Zuhair or what?
Yes.
Okay. So I have to, you know, we have to move a little bit, faster. Let's go to the other important part of the course, which is the, which is basically the frequency response. So what we want to do now, the rest of this lecture, and we'll continue in the, you know, frequency. Okay. Okay. Now what we want to do, we would like to go to the frequency domain. Okay. And we'd like to have the plotting in the frequency response. We are going to have 2 types of plot, one the polar and one is logarithmic body, which you already have studied in, you know, I think in the electronics course. Okay. So basically, what is a frequency response and why it's important? Why it is important to do the frequency response? Any suggestion?
Well, of course, it's important in certain applications, especially in communication.
Okay.
You want to, for example, in modulation, for example, when you want to see the modulation, you do modulation for the signal, incoming signal. You want to see which frequency
This is in communication. How about control? What's the importance in control?
Also in sampling, Doctor. Maybe sampling. I don't know if we have sampling in the.
What's important in control system? The frequency domain. One advantage is that you could have, I mean, you could identify your system from a data, and the data is good for the frequency response manipulation. The other one, we will use the frequency response in the design of controller, because we can design for steady state as well as well as the transient. The root locus usually it is deal with the transient. However, in here we'll see that we are going to do, you know, we could have when the design will, you know, address both issues of the steady state as well as the transient. Now the question is, what's frequency response? What is a frequency response? Can you tell me?
It's the Fourier transform of the Fourier transform, doctor, of the and then you basically take different
any other thoughts?
To know the frequency where the system can work properly.
Good thing. This is advantages. But what is exactly? Okay. Suppose,
It's like it's
Yes,
it's like
magnitude.
the
like what?
it's like the Laplace transform, but the real part, but only the real part of S.
That's correct. You are absolutely correct. However, this is not what I'm asking for. Let me ask you in here. You have a circuit, okay? Suppose I have A sine omega t. What will
yes.
the steady state output?
Steady state will be A.
Will be A?
Really?
Well, A over 1 plus maybe omega square or something like this. I don't
Shabab,
know.
Could
The
be
Laplace
really.
transform.
any other thought? Any other thought? You are taking, Shabab, come on. This is in circuit 2. You
The
are,
output is the periodic with the same frequency.
what? Say that again. You are, that's correct. The output will be another sine if you have a circuit, the input to the circuit is sine wave, and the output will be another sine wave with different magnitude and different phase. Both the magnitude and the phase are function of the frequency. And you have taken this in circuit. Go back to circuit and look at it. So a frequency response of a system defined as the steady state response of the system to a sinusoidal input signal. Okay. The way we do it, yes, we assume that S equal to j omega. We don't consider sigma, but this is, I mean, this is the formal definition of the, frequency response.
Usually, doctor, when you want to plot, you just take the Fourier transform of the function in time domain.
Why do you take the Fourier transform? You are in circuit 1, circuit 2. You don't have any sigma. It's, look, simple. Suppose I have, this is my signal,
Mhm.
which is sine, isn't it?
Yes.
Present sine. And suppose this is the transfer function.
Yes.
I need y of t. How do I find y of t? First of all, I need y of s. Y of s equal to what? T of s, r of s.
Yes.
How do I go to y of t?
Take the inverse Laplace transform.
Exactly. And how do I do it? I multiply those two and do partial fraction. So this is what I will do. Now I invert to the time domain. Assume my system is stable. So I will have constant time P1 t, minus P1t and so on. So at steady state, what will happen to those terms?
Zeros.
They will all
of them
diminish.
Will vanish.
will vanish. And I will have the Laplace inverse of s plus beta, s,
Which is cosine maybe, doctor.
which is sine and cosine, or
Yes, yes.
combine them. Because look, I mean, if you take simply s plus beta over s square plus omega square, assume I don't have any
في
constant.
واحدة S over S square واحدة B over S
Exactly.
square.
S square plus omega square
مظبوط.
plus
واحدة cosine واحدة sin.
beta over s square plus omega square, which one of them sine, the other cosine, combine them. That's where the phase shift will come. Okay? So, as I said, the frequency response, basically it is steady state.
Mhm.
To leave the system to go to steady state and then you will work in there.
Yes.
The way to approach it, as I think Zuhair mentioned it, that you let S equal to let S equal to j omega.
which is the imaginary part, not the real part.
Yes.
Because the
This one in
Laplace
circuits.
transform.
Wait. Where do you use this one in circuits?
We use it in circuit too, as you mentioned, in the RLC circuits. If we want
يا
to
لا
analyze.
قول لي عبد الرحمن لا تلف الدور علي في
أبشر.
اسم particular اسم شباب.
Particular.
Phasor analysis. What did you do in phasor analysis?
Yes, we convert مثلا ال L to SL. هذا قصدك؟
اي بالضبط هو phasor analysis. We call it phasor analysis.
Yes, exactly. مثلا ال C1 over G omega C.
Exactly. This is the phasor analysis.
Yes.
So I would like, يعني what I'm trying to say in here.
Try to connect everything.
Exactly. I want to connect it to what you have already. It is not new. Nothing is new.
صحيح.
Already.
Yeah,
This is just a notice, Doctor, that Laplace is a general case of the Fourier because Fourier is just related with the omega.
Exactly. You are right. You are absolutely right. يعني the Fourier is going to be a subset of the Laplace.
تمام. So if we have, for example, a function in time, and we want to get the function in omega in the as a function of omega, we do the Fourier transform, and then when we plot the function in omega, we can have the frequency response.
That's correct. That's exactly what we are.
So it depends on application. But in this case, as you mentioned, we have the function already in S, so we shouldn't go to the time and then go to by Fourier. Now we can just ignore the real part and substitute the G omega to get the frequency response.
Exactly. So basically, look. Now, G of J omega is a complex function. I would like to represent this function. Okay, how do I represent it? You have a complex function. So either you will use the Cartesian representation. That's basically, I will have the real part plus the imaginary part. This is one way. The other way is to represent it by a polar. That's basically magnitude and an angle. Okay, and of course they are related. The magnitude equal to the real part square plus the imaginary square and root of that one, and the phase will be tangent inverse of the imaginary over the real. Okay, so what we are going to do, we are going to use again graphical methods in studying the topic. I will be having, okay, two types of representation. The first one is the polar plot. In here, suppose I have the S-plane. So I can write, this is the real part, real, imaginary. This is in Cartesian representation. I want to do the polar in here. So let me assume this is my reference. So this is the, what is the angle will be in here? And this in here. What will be the angle? In this axis, in this side of the axis. Will be zero angle, isn't it?
Yes.
What about the angle in here?
90.
90.
Imaginary part 90.
180, 270.
ممتاز.
Okay. Now, suppose I have the points 1 and 1. Let me represent it in the rectangular representation, where this point will be. This is the one real,
The first,
one
in the
imaginary.
first quadrant.
This point,
Yes.
1 and 1. If I want it to be in polar, what will be the magnitude?
Root
And
2.
It will be root 2.
And the
And the
degree is
angle will be
45.
45. And where is that?
يعني just
This point.
vector.
Okay. So this point, I'm representing it in polar or in rectangular. We will be using the polar when we go to Nyquist, and we will be spending a lot of time in doing the polar. Now, let me do the body. Body plots. What do we have in body plot? Body plot, basically, you will have two graphs. The axis will be log omega. The The first one, the magnitude 20 log of the magnitude, which we call it dB, and then the phase. So I have two graphs, one on top of the other. And this is, you have done it what? In electronics. I don't know how much, honestly speaking, I don't know how much you have done in electronics.
والله
In
دكتور يعني
213.
ترى very shallow.
Okay, okay. Now we are going to go in detail. The body plot is very important in the design. In stability, usually they don't use it a lot. There's certain degree of vagueness, even though we can conclude, but generally speaking, we don't use body plot for the checking the stability. Usually we'll use the Nyquist. So let's start with the body. We will come to the polar after we finish the body, because the polar is associated with the Nyquist test criterion. Now it's Nyquist stability criterion. So let me start with the body plots. In body plots, suppose I have G, which we have said it's complex. So it has a magnitude and it has a phase. Okay. Suppose I have, okay. So the body plot, as I said, we are going to have the magnitude in dB, 20 log of the G of J omega versus the log omega, and then the angle versus the log of omega. So now, first of all, we will be using the, you have to be familiar with the semilog graph paper. The y-axis is regular scale, that's why we are calling it semilog, and the x-axis is log omega. Usually, this point, we don't start from zero. Why not? When we use the...
في minus وفي plus.
We will not start from zero in here. In the real, in the, you know, the horizontal axis. Why?
In the horizontal or in the y-axis? لأنه ما يصلح ما في log
The
zero.
y, there were no problem. The problem with the x-axis.
Yes, because the log zero is undefined.
Exactly. So usually we will start maybe 0.1, 1, 10, 100, and so on, or maybe 0.01, and so on. So you never start from zero. And this is, each cycle is 1 decade. It's factor of 10. Please try to be familiar with this type.
So we have covered that, Doctor, in electronics too.
Okay, great. So
and also in circuit 2.
Okay. Now, suppose I have the circuit, and I would like to get the frequency response for the circuit. Okay. This is the output V2 over V1. This transfer function, very simple, voltage dividing rule. So if I need the frequency response, I replace S by J omega.
J omega.
So this is going to be V1 of J omega over V2 of J omega, which is equal to 1 over J omega RC plus 1. What will be the magnitude? 20 log. First of all, the magnitude. Equal to what?
It's the 1 over root square 1 plus omega squared R squared C squared.
Okay. What about the angle?
Tan inverse.
Minus, because
minus tan inverse.
Of omega RC. I can take 20 log of this one. Okay, if you take 20 log, this is what you are going to do. And now, this is the...
Doctor, not omega RC. Omega 1 over RC or something like that. Yes, yes, yeah. You are right.
There will be, yes.
Yes, that you are right.
It will be RC, okay. There definitely it should be functional.
You are right. You are right.
Oh, no, wait. Tau, I represent, okay, look.
Yes, yes.
Tau, okay.
Which is a time constant. Yeah.
Okay. Okay, now let me make a graph. This is magnitude, this is the phase. Suppose I have, okay, this is omega, magnitude, and phase. Let me take omega equal to 0. What will be the magnitude?
It'll be -1.
And in dB, okay, in dB. From here. So this will be
log 1 0.
Angle
0 again.
0. Suppose omega equal 1 over tau. عبد الرحمن because انا ابغى اشوف شباب باقيين are they around?
Minus y over 4 يا دكتور.
Just one second. Ali. How many Ali I have? So كل علي ما موجود، ايش كم علي عندنا؟ شباب we have at least 2 علي.
ايش علي دكتور؟
3. and none of them around. شكلي انا وعبد الرحمن بالكلاس. كيف؟ مين معي؟
كان يهرم دكتور؟
مين معي؟ علي العيسى ولا مين معي؟
علي الجنيبي.
علي الجنيبي. طيب يا علي، الحمد لله انك موجود. How about the other 2 علي؟
Yes, here, علي العيسى.
which علي now؟ هو السابي ولا وين؟
علي العيسى دكتور.
علي العيسى، ما شاء الله. طيب يا العيسى، if omega equal to 1 over tau, what will be the magnitude in dB? What will be this one?
-10 log 10 2.
Okay, which is basically 3 dB, -3. So
-3, yeah.
So okay, and what about the angle?
-45.
Exactly. Thank you. Now let me go at extreme. If omega equal infinity, what will be the magnitude? What will be the magnitude? Minus infinity, and the angle will be, what will be the angle?
Minus pi over 2.
Minus pi over 2. Okay, so let me sketch it. This is the graph. What type of circuit we have in here?
Low pass filter.
Low pass filter, exactly. This is low pass filter. Okay. Now, look, this circuit which we have is very simple. We have done it. What will happen if I have a complicated system? A system where I have the transfer function has a constant term, it has zeros, poles or zeros at the origin, simple poles, complex conjugates. Okay. Suppose I have, this is my transfer function. This is very complicated. What I want to do, I would like to do, a sketch, and I would like to use, some straight line approximation. So we will be using 20 log, because if you use 20 log, what will happen? If you use log, okay, log scale, what will happen to the factors in here? What will happen to the factors in here if I use the log?
divide by 10 يعني ولا كيف ايش قصدك؟
No. Suppose, okay. Suppose I g of j omega equal to, let's say, 10 over j omega plus 1. And I would like to use, what's the magnitude? The magnitude is going
100 over omega square plus 1
10.
underscore.
Why 100? 10 over root of.
طبعا هي 100 over square root يعني بس 10 في النهاية صحيح.
Okay, if you take 20 log of the magnitude, this will be what?
So it
You
will
can
be
separate it as basically negative 20 log 10
So basically,
minus
it will be, summation or subtraction of the factors.
subtraction, yes.
indeed.
Yes. So what we are going to do, we will be using, if we use 20 log of this one, which will be the same as 20.
Yes. You have 20 log the numerator minus 20 log the whole denominator.
Basically, is going to be the components, adding the component together. So I'm converting this complexity into simple addition or subtraction.
ايش دكتور الفيرب الترمينولوجي هذا would be a formidable task.
Which one? Okay.
ايش هذا
Basically, if you want to approach it without the approximation, without the log, it will be very complicated. This is in this sense. This you should understand it. Yeah, it's almost impossible task. Okay.
Means complicated. We complicate ourselves.
It will be complicated. By converting it into, log, I will deal with the, one term at a time and add their effect. This is interesting for the magnitude, while for the phase, it is automatically, how do I get the phase for the system? The summation of the angle of the numerator minus the summation angle of the denominator, isn't it? For the phase, sorry, is going to be the summation of the angle of the numerator components minus summation of the angle of the denominator components. Do you agree? So I don't need the log for the phase. The phase by itself, it lends itself to the procedure. Okay? So now let me study each component. How do I sketch each component alone and then add the effect together? That's basically, if I have, what are my components? What are the components? Basically, I have a constant, a pole or zero at the origin, simple pole, simple zeros, or I could have simple, I could have complex conjugate poles, complex conjugate zero, sorry. And this is simple poles, complex conjugate poles. So what I have to study, basically, those type of factors. I will make the graph for each individual term. Then if I have transfer function, put them together, add them together. Any question? Any question?
Victor, can you go back, please, to the
Okay.
function?
Here or before?
Simple pools.
This one?
Yes. Is this
Okay.
is this simple pools or complex?
What did I say?
This one, the first bracket.
Okay. This one?
This is and then the denominator.
Are you talking about this?
لا اللي جنبه.
عند الزيرو.
يعني لا البول اللي قلت عنها عليها سمبل بول هذه مو
Yeah,
المفروض
this is simple pole or this is simple zero. I could have, this is complex conjugate. I'll have two,
طب هذا مو المفروض
Conjugate.
كومبلكس بول هذا؟
they are complex, they are coming from a complex, basically look, if I have, let's say, a term s square plus 2 zeta, let's say omega and s plus omega n square. Let's say omega n square in here. Now substitute for s by j omega. What do you get? This is omega n square. This is going to be minus omega, well, j omega, sorry, j omega square plus 2 zeta omega n j omega plus omega n square. But look at what is this one? What is the j omega square? What's correspond to? So this is going to be omega n square, and this is going to be minus omega square, isn't it?
Yes.
Okay, plus 2 zeta omega n. This is j omega plus omega n. Now divide square. Now divide by omega n square, and you will get this term. Divide by omega n square. What do you get in the numerator? You get 1.
1
What about this one?
minus omega square over omega n.
Okay, but this one will give me, so I will have 1 over omega n in here square 1 minus omega over omega n, the whole thing square plus j 2 zeta omega over omega n. This is basically what we have in here. This is derivation. This is how do you, this is what we call the complex conjugate. Is it clear?
دكتور البول هذا اللي هو 1 بلس j اوميجا تي ام
Yes.
هذا البول مو هو المفروض البول جاء على تي ام؟
مو المفروض يكون what?
البول هنا اللي هو 1
أيوة.
بلس j تي ام
Yes.
هذا مو كومبلكس بول.
This is, look, what I'm saying in here, what we are going to do, we are going to do approximation. This is come from this equation. Do you agree?
Yes.
Come from this equation.
لا اتكلم عن الترم اللي جنبه دكتور على اليسار.
اللي قبله
اي هذا
simple.
هذا مو كومبلكس.
This is simple. هذا مو complex.
لانه جاء على تي ام.
Look. هنا multiplication. You are multiplying many. Look. It is 1 over, let's say, s plus 1, which in the is going to be 1 over j omega plus 1. So it's simple.
Okay, it's clear.
Okay. So now look. I will have the factors. Okay, let me assume I have k, a constant. What will be the magnitude of the constant? What will be the magnitude of the constant?
The constant.
Constant. You just take 20 log of that constant. If I want to sketch it, this is log omega. How does it look like in here? It will be a straight, just a constant. What about the angle? The angle will be 0. What will happen if I have a negative constant? What will be the magnitude?
It will be positive because
Okay.
the
What about the
magnitude,
angle?
magnitude must be positive.
Okay. So
the angle will be 180.
180, exactly. So this is basically what I'm saying. If k is a constant, in this case we are taking it to be 20. So take 20 log of, okay, take log of 20 and multiply by 20 and sketch it. This is for positive, the angle will be 0. For a negative, the same magnitude, but the angle is going to be 180. So now this is one term. Okay, next time we'll go and see the other term and we will, draw each one individually, and then the overall transfer function is going to be, okay, we will, okay, in the overall transfer function, we will, add all those terms. So as I said, we will continue by the other term. So far, we took only the constant term. Next time, we will take the simple, well, we will take the polar zero at the origin. We will take the simple polar zeros, complex conjugates. Thank you.